this talk is going to be, it's about evaluation, and I want to basically highlight some problems that we've observed regarding evaluation in a couple of settings and solutions that we're providing with a human-in-the-loop approach. Now I want to preface by saying that evaluation is somewhat, it's a means to an end, and for me personally, this end is to try to enable us to build systems that are able to summarize information better for people. And what I mean by this is in a couple of different dimensions. So one approach is I'd like, in sort of this knowledge-based population setting, I'd like to basically be able to view a summary of a particular entity. Here it's Carrie Fisher, who played the role of Princess Leia Organa. And I'd like to have a short summary about what her occupation is, where she was born, what some other information about her as a person. In another setting, I'd like to be able to answer questions. And I'd like to have a question like, can I reuse a deactivated SIM card without actually having to read the entire manual? I'd like to be able to summarize this answer as simply no. Or I'd like to be able to also summarize more open-ended questions like reasons why fossil fuels are bad, because burning them releases a number of extremely harmful gases, et cetera. And so in this latter case, it's less, it can't fit well into a slot, but we have a more open answer that we want here. And of course, if I say summarization, that's not complete without actually wanting to be able to summarize documents. And in all of these settings, though, we have some systems that exist today that do some amount of a job, and I think it would be fairly non-controversial to say that it doesn't do nearly as well as we'd like them to. There are a number of reasons for this, but one of the problems that I'd like to sort of address is the problem of evaluation. And the kind of way I see evaluation as the way we think of it today, the way it sort of came out or the way we've sort of formulated it, makes a lot of sense in the setting of classification where we can come up with this evaluation data set. So we have a number of inputs, and for every input we have a nice goal label for it. And this goal label fits into a small closed class. And so when a system produces an output, it also predicts within the same closed class, and it's very easy to tell whether or not the system got it right or wrong. But in all of the cases, all of the examples I've shown you, we're actually generating some output. And so the sort of evaluation data sets that we construct, we don't call them gold answers anymore, we call them reference answers, because there's some arbitrary string that's, again, open class, and it's very hard to tell whether a system has matched it or not. We know kind of if a system produces the exact same answer, exact same string utterance, as in our reference data set, we know that's probably good. But in all other cases, we really don't have a good idea. To see where this actually creates problems, I'd like to revisit these tasks. So here's the entity summarization task, and this is what we have in our evaluation data set. This is true in, let's say, the TAC KBP setting, as well as many other kind of knowledge-based population evaluation data sets or tasks. And we might have two systems, one that predicts that Carrie Fisher is a writer, because in between the two Star Wars movies, she was a writer. And we might have another system, and this is, in fact, I will have to report this is true of the Stanford system. We might identify her to be a princess for somewhat obvious reasons, because she played the role of a princess. And we need to be able to compare which of these two systems is better, which of them is actually extracting the right sort of facts. And because this new fact of writer or princess is not something that's part of our evaluation data set, we simply have no automatic way of determining which of these two is correct. Currently, the way we evaluate it, we say both of them are worse and they're equally bad. And this is, I think, this is the kind of root of the problem. When it comes to question answering, where you have this nice answer no, this is part of the MS Marco data set, and the answer no is in the reference data set, it turns out the systems produce answers like yes, which maybe we could identify as not being no, and an answer like once a SIM card has been deactivated, it can't be used again. Clearly, the one on the right is a correct answer, but there's no sort of automatic way of determining this. The automatic metrics we use right now are based on rouge or some form of word overlap, and both of these are considered to be wrong. In text summarization, it is still a giant mess. It's been a giant mess for a long time. because the summary that is produced by a system can be so dramatically different than that produced in the reference data set or the reference answer. And we try to make some sort of comparison based on some form of word overlap. Think of, again, Rouge. And it turns out that just last year there was a system that produced, the one on the left is the baseline system. The one on the right is they augmented it with a reinforcement learning objective to try to maximize Rouge. And they find that it indeed does improve Rouge scores, but the way it does it is by appending a bunch of random junk at the end. You can see why this might improve your word overlap scores, but this is clearly not the intended result. And kind of fundamentally, what we would like to get from our evaluation methodology is to be able to say, here's a bunch of output in one system. These are where it does well, it does badly, and this is of another system, and be able to compare them. But unfortunately, because of these problems in comparing the system's generated output with the reference answer, we don't actually know what the judgments of every example are. There are a lot of things which are simply unknown. And this is, I view this as saying that the evaluation data set is incomplete. But the kind of nuanced problem is that what happens is now that your evaluation and hence your system development is biased towards things that play well with the reference data set or play well with the sort of automatic metric you're using to compare with the reference data set. And so this is the sense in which I say that there is bias in our evaluation. And this bias is not something that people are not aware of, but I think in some senses, some places it hasn't been as well quantified. And for this reason, human evaluation is often considered to be the best approach on all of these tasks. And the kind of framing of my work is there some way we can go from something that we know is correct, human evaluation, and make it cheaper and hence more practical to use without introducing bias? I mean, we could go all the way and just use this sort of automatic evaluation that exists, but that, as I say, I claim is introducing bias. So I'm going to look at this in two settings. The first setting is in a very nice and structured setting of knowledge-based population. And the structure is basically something we can exploit to get what I think are good gains. In the second setting of natural language generation, it's a little murkier because we're dealing with text. There's very little structure we have that we can exploit. And we're going to show that there are some sort of fundamental limitations in terms of how much we can reduce costs. So the first work is with my wonderful collaborators, Ashwin, Percy, and Chris. And this was the EMNLP last year. Just to give a setting of what exactly I mean by knowledge-based population, because some people have some different perspectives. You've seen the goal of the task is given an entity query. I want to be able to identify a bunch of information about them. And the version of this task that I'm going to restrict myself to is we're constructing this sort of knowledge-based entry entirely from text. So we have a set of text documents, and we want to populate this entity summary, and not just for this one entity, but we want to be able to sort of create this relational graph between different entities. So we want to have a summary for Carrie Fisher as well as for Debbie Reynolds. Just to look at what this means at the sort of textual level, suppose I come across this paragraph that mentions this person, Carrie Fisher. I want to identify that Carrie Fisher is actually this global entity that is this person I represent with a photo. And from other parts of this text, I want to identify facts like she was an actress or that she died at a particular date. As you go through other parts of the document, I want to be able to link up entities. So when Fisher is mentioned in the second article, I want to know that that Fisher is referent to this, again, global Carrie Fisher, and hence construct this sort of knowledge graph. I don't think I need to pitch it to this audience, but knowledge-based bases are, of course, really useful. And they're ubiquitous right now. When you Google for something, you do see this sort of entity summary I was talking about. And we also know that they have a lot of potential for use in many other tasks, from question answering to reasoning, et cetera. I will still stress that while knowledge bases are so we know their value and power, the sort of goal of automated knowledge-based population is still a very, very challenging task. And As a sort of reference is in the sort of shared community task of TAC-KBP, the Stanford system is one of the top-ranked systems, but we're still only half as good as the human system or the human participants. And we've been sort of struggling with how do we like make that gap smaller? How can we be a little less embarrassed about our performance on this task? And while we and I have definitely I've thought a lot about this, and there are many reasons. One of the reasons I think we uncovered through this work is that actually the way we're doing our system development is really difficult because the evaluation is biased. So for the rest of this section, I want to kind of make the case of why or how we can, where that bias comes from, how we can measure it, and then talk about our solution, which includes humans in the loop. So in order to give you a sense of what I mean by bias, I want to give you a sort of statistical perspective of what's going on. So instead of thinking of this as this collection of documents, I want you to think of this as a space, a universe of relations. Every point in this universe is a kind of triple relation between an entity and an object, like Carrie Fisher, an actress, with some relation, like employed by or occupation, title. And it also includes the text snippet from which this fact was extracted. I'm going to call this just a relation instance. And of course, there are good instances and bad instances. And a system produces a subset of this space. We are going to evaluate the system based on precision, just what is the good stuff what fraction of the stuff it extracts is good, and recall, which is what fraction of the good stuff does it extract. This is all very standard. Just the kind of caveat is this space of possible relations is gigantic, and we can't possibly annotate it exhaustively. We did a sort of back of the envelope calculation, and even if we were trying to exhaustively annotate this sort of medium-sized corpus of 100,000 documents, it would be more than $1 million. And so the way we've been doing evaluation so far has been in sort of one of two modes. The first mode has been to sort of restrict ourselves to look at a very small subset of documents. So if you're familiar with the ACE or muck tasks, that was sort of in this light. And the problem here is that the subset of documents that we identified are not large enough to properly evaluate the performance of the system. In some way, you can think of it as not being an adequate sample of the system's output to measure precision. And so we found that when you have systems that are simply trained on this data set and you try to run them on the wild, they end up having very poor precision. The take that has been adopted by the TAC-KBP competition has been to sort of crowdsource the process of identifying relations. So they'll ask all of the systems that are participating in this competition to propose what they think are true relations. And then they'll get LDC annotators to actually identify and annotate and label them to be correct or incorrect. Now, this is great because it's much cheaper to do it in this approach. And so you're able to annotate a lot more data. But it's terrible because when you have a new system that you're trying to evaluate on this data set that's been collected, it's going to have this really weird behavior in terms of how its precision is measured, because it's precision relative to the other systems that have participated. And recall is also something that's quite funky because it's relative to the other systems that participated and not indicative of the true recall. And so there's a question of there are more than 60 systems that participate in these competitions. Is this bias actually significant? And we have a kind of we have a natural experiment that I'm just going to quickly kind of give the intuition of. So in the competition, every system's output is exhaustively annotated. So we have this kind of true condition. What if we knew what all of the output of this system, how it was evaluated? We can run this counterfactual experiment by basically taking one system out and constructing an artificial evaluation data set, omitting the results from just this system, and then compare what that score would be. And so this is a way for us to get a measure of what this bias would be. And we're able to run this on all of the systems from different teams on the 2015 slot filling competition. And so the way I'm going to present the results is on the X-axis are the different systems. On the y-axis is the sort of true score measured by macro F1. And so these black dots are kind of what's published. This is the results that we should expect. And when you do this leave one out experiment, you see this dramatic drop in scores. Because each of these systems is identifying a very unique set of relations. There's a heuristic called the AnyDoc heuristic, which basically ignores the source of a fact. It just considers if you've predicted that Carrie Fisher is an actress from anywhere, then we're going to consider this fact to be true. And we still see a gap. Yeah?
Sorry to interrupt, but I'm struggling reading this graph because I guess I would have expected as the number of systems increases, the macro F1 would go up, but it's going down. So.
Right. So this is not the number of systems that participate, but the index of the system. So this is the top ranked system, and this is the worst ranked system. It's not an experiment where how does this bias change as the number of systems changes?
It's not cumulative along the.
It's not cumulative. Yeah.
It's on a per point basis.
Correct. Got it. And so on average, the median kind of bias we observe here is about 2% F1. One of the things I just want you to notice is that the top rank systems actually have a much larger bias. And this is going to be part of the theme. So to give you a context on what that 2% bias is, for most people within the kind of community, we think that, if we have a system and we're able to do some improvements that gives us a 1 F1 point improvement, we think that that's significant. And if it's less than this bias, then it means that these improvements are very hard to identify. But more importantly is that this bias is very systematic. It's not like it's not noise. It's if you have any system that produces more novel facts than existing systems, you are going to penalize it more, which is why the systems at the very top ranked systems have the largest bias. And the consequence is that if you're trying to empirically tune your systems, you're going to overfit to predict only what's already been seen. How do we fix this problem? So I will posit that the kind of fundamental problem is the fact that we are not adequately representing the output that comes from the system. And so it's very hard to sort of construct one static evaluation set that will do this. So we essentially need to be able to annotate the predictions made by system on demand. And so if we were able to do this, we have a very simple approach to compute, let's say, precision. We sample some output that comes from a system, and we get them annotated, let's say, by crowd workers. Once we do this, all we have to do is take the average score of how many of these things that we sample were correct. And so this simple average we know is an unbiased estimate of the precision of a system. And so we know that's going to be correct. We know we can also get these annotations done fairly cheaply using crowdsourcing. And so very unsurprisingly, we see that there is no bias once we take this sort of simple sampling approach. One of the problems is that it does increase our variance. It's hard to really say what variance is when you're not even, when you have a very, like when you're using the original biased estimate, because that's not even a valid estimate. But I'll address how we can reduce the variance of the estimate for precision in a bit. We can also ask ourselves, can we actually measure recall in a sensible fashion? The way that recall is measured currently is based on how many relations you extract that have been extracted by other systems, which is not even a representative of what the true recall in this data set is. And so if we had some way of sort of randomly sampling from the set of true relations, we can simply ask ourselves, how many of those true relations are predicted by the system? And if that's the case, then we have an unbiased estimate for recall 2. In order to get this like sampling across the true instances, we don't know what that set is, but we make this one assumption that these true instances are uniformly distributed across documents. So if we picked a random document and then had it exhaustively annotated, we'd be able to work backwards and compute what that uniform distribution should look like. And so in order to do that, we have a little bit more involved of an annotation approach. We have to have people find out what the entities in documents are and then actually go through and predict relations between them. And so this costs about an order of magnitude more than simply telling us what the relation between a fixed set of entities are, but it's still something that's feasible. And again, you should not be surprised by this, but we are able to eliminate the effect of bias on recall. And I mentioned that variance is sort of still a problem in this setting, and so the kind of fundamental thing that I've left out is I've said we'll take for every system, we'll draw a set of samples and compute precision and recall. So how can we reuse these samples is the kind of approach we can get to sort of save on data. And that might seem like a very simple ask, but the kind of key problem or the obstacle in doing this is if you were to just take two samples that you collected from two systems and just take the union of these two sets, what you're going to end up is with some region that is overlapping between the two systems that's going to be oversampled. And so this is going to end up giving you a more biased estimate. There's a kind of standard approach to try to resolve this, which is with importance sampling, where you try to basically reweight the samples in this overlapping set. And that's kind of the approach that we're going to take. There's one caveat that you have to sort of address with standard importance sampling, which is in importance sampling, the kind of methodology is you describe one proposal distribution. The simplest proposal distribution is to uniformly sample relation instances from the different systems. And then you basically construct this, you construct a sample from that distribution, and then you reweight the samples by the ratio of probability. So this PEA by Q of X. Now the important problem, or well, the kind of crucial factor in executing importance sampling is that you need to draw your samples from your proposal distribution. Now, if you have new systems that are sort of participating in your evaluation, your proposal distribution is also going to change. So instead of being uniformly drawn from systems A and B, it would be uniformly drawn from A, B, and C. And so all of the samples you've collected thus far would become invalid. And in order to sort of address this problem, we basically have to kind of fix this kind of integration procedure. It's a little, well, so in the kind of estimator that we propose, the kind of key intuition is that we're able to draw samples independently from each system. So the way I have this written out here in sort of math is that I'm drawing an independent sample from system A and from system B. If I had system C that comes along, then I have an independent sample from system C. And then I reweight these samples with a similar sort of reweighting score. And if you look at that score for any one system, it doesn't make sense. But if you take the sort of expectation across all the systems that you're including, it will give you an unbiased estimate. All of this is a lot to say that we can basically reduce the confidence intervals for our estimates of precision by a factor of 2, which is equivalent to having 4 times as much data. So that's the main win if you're able to combine the prediction from different systems. There's another question about what do we do in the setting of recall. And here, I'd like to again stress the fact that the systems that are participating in our evaluation are not a representative sample for all of the true relations in this space. And so in some sense, we can't avoid the fact that we need to get some samples from this true space Y. But we also have a lot of data here. Is there any way we can reuse it? And the kind of key intuition as to how we might be able to do that, and sort of the estimator we'd write down, is that we can factorize this recall estimate, which is how much of the system predicts that's part of the true set, as being a combination of pooled recall and pooled recall. So what is the expression on the left? The pooled recall is how much does this system extract relative to all of the other systems that participate. This is sort of the TAC KBP recall that we had. And on the right-hand side is sort of just is how do we adjust that recall to basically ask, if I took all of the systems that I combined, what fraction of true instances do they identify? And so on the left-hand side, we can use the same sort of importance reweighted estimator to get a better prediction of the pooled recall. On the right side of the pooled recall, we stick with a very simple, take a random sample from documents, and using that random sample estimate recall. On this setting as well, we find that we're able to almost have the confidence intervals for estimations of recall.
Could you explain how the two definitions for recall factor in when you're computing your importance sampling distribution?
So you only consider the importance sampling distribution when you're doing the pooled recall here. And so when I'm estimating the pooled recall, it's sort of on an orthogonal set of, so I have a subset of documents that I have sampled that I have exhaustively annotated. And so this random subset is like the subset that I use to actually sort of, if I had any one system, I could measure what its true recall was on this subset of documents. Does that make sense?
This is like the true distribution.
This is the true distribution.
And this is a proposal.
And so this is another proposal. So these are two terms, and literally the recall can be written as the product of these two terms.
Okay.
This right-hand term, and they're computed on sort of independent sets, so we can literally take that product. The one on the right-hand side comes from this random sample of documents. The one on the left-hand side comes from, the way we're measuring this is based on the annotations that we've collected for every system, right? And so in that setting, we have this kind of overlapping bias problem. And so we have the importance reweighted estimate here. It'll look very similar to the expression we had in the previous slide, but some things have to change because we don't know what P of X is.
I actually have two questions. So to measure recall, you made this assumption that the instances are distributed uniformly across documents. If you were in a setting, something like KB completion, where you don't have documents to tie every relation back to, is there an alternative you would do, or would yield be the right measure?
Could you?
The yield of the system as opposed to recall estimate based on.
So I think that's a very important question, and it comes down to how we want to measure our systems. I mean, while yield is a very good and informative measure, recall is I view it as being a sort of approximation where, because it's very hard to measure recall, we use yield as a proxy. And recall gives us a better sense of how much room we have to improve, right? We don't know what the upper limit on our yield is. And if we did, then we just take that ratio and we'd get recall. In the sort of KB completion setting, so I think I might need to take a little bit of this offline to discuss kind of what what we can make an assumption of. But if there's any way where we can get some signal for a random sample across possible links. Now, in the KB completion, it's a little difficult. You could maybe ask, like, is there a link between these two entities in your graph? And then have people do some search or something to figure that out. That might be a way to get a handle on this. But it does require, I mean, I think KB completion is a little more difficult to do sort of human evaluation in, because it's hard to sort of tie it down into a particular document that someone. So the advantage we have here is we can always show a person this snippet of a document, and on average, everyone is able to identify a relation, whether that relation exists or not. And so it's sort of very objective to make that judgment. That makes sense?
I'll save my question. Next one for later.
I just want to sort of, I've described everything as being, I phrased it as how we can reduce variance. You can sort of turn this around and ask how many samples you need to collect. You can use a sort of upper bound to decide how many samples you want to collect. And if you're able to reuse systems, you can basically amortize the number of samples you collect. That's the main takeaway, and you'll save an order of magnitude versus collecting independent sets of samples. The final thing I'd like to say about this whole approach that I've described is that I've kind of given you here's the kind of theoretical insight, and here's a nice cute estimator. But we've actually tried to build this out into a practical framework that people can upload their own systems to, and we'll take care of doing all of the funky sampling, addressing all of the quirks of trying to do KBP, and actually sending out jobs on Amazon Mechanical Turk. And in order to do this, to give you a sense of what I think is practical about the system, is right now we had when we were running this, there was no systems that participated. We were the first, and cost about $150 per system, and it took about 30 minutes to evaluate one system, because it turned out that these tasks were things that annotators got to really quickly. So the summary of this section is that we looked at this task of KBP, kind of looked at how there's this problem of bias because of how we sample our evaluation data set. And if we allow ourselves to annotate predictions from systems, we can correct for this bias. And if we try a little harder and basically write down a sort of importance reweighted estimator, we're able to reuse samples and actually try to make this system practical. I'll now move into a much more difficult setting where we're trying to evaluate natural language generation. And this is joint work with Steve and Percy.
Now, so first, recall our one point on the PR curve, right? If your system generates a whole list of relations, then you can measure it on the whole list. But ideally, you want to see how its performance degrades as things go down. Do you think this would extend to, say, area under the curve or other metrics that are above the whole trade-off?
It very well. So one way of viewing this is that here you're just basically you can look at your recall on all of your all of the output. So as far as your recall estimate is concerned, you can basically take it when precision is at its minimum, what your recall would be. And so that gives you that point on the curve. And for the other points in the curve, I think it would be possible to extend this approach where your estimates of precision, you want to basically be sampling in the right way so that you are able to estimate what that precision would be at different sort of thresholds. And so I can imagine there's a way to sort of set that up to give you a kind of estimate of what AUC would be. I haven't thought too much about it, but that's my intuition.
So another question. So the original goal was to improve our evaluation so that we can build better systems. Have you seen, how can you imagine, because it seems to me that you're paying $150, you wouldn't be able to pay this price every time you make a tweak in the system.
You're right.
Use it during the system build. So how do you think this will reflect on improving the system?
You're right. So I'd say a couple of things about this. So one is because we're reusing these systems, it's very, if you have two sort of dev iterations, 90% of these relations are going to be identical. And so you're really going to be sampling a very small incremental subset in order to estimate your scores. So the cost of 150 will be much smaller. The other aspect is kind of how this fits into the training loop. This is something I've thought, and I don't feel like we necessarily have the most convincing answers, and we haven't actually built a better system using this methodology, right? A couple of things to note are, this is when you want to basically, this framework does make it easy for you to sort of try to do your hyperparameter search with a more accurate dev score. The way you would do this hyperparameter search earlier would be sort of trying to force your system to predict exactly what other systems predicted, which is not really what you would want. And so this is certainly at least helps you when you're doing your hyperparameter search. Other aspects that I think when you're doing system development, you certainly want to have this score that gives you some objective truth, but you also want to have some sort of interpretability. So as a human being, you can sort of look at this and say, these are the things that I need to improve on. some things where this framework does help, and this is sort of on our webpage. You get sort of free annotations on like what your system output was, where it did well, where it did badly. You can also break that down by relation. I didn't describe the details of this, but the reason why my estimators had this P of X kind of thing in front of them was how you actually weigh how you pick which samples from a system to annotate. And you can sort of play around with that to get estimates of what your performance is on every single relation, as well as different sort of folds of it. So you can use this to get good estimates of different kind of summary statistics of your performance that could help you guide your model development.
Another question: have you measured the bias that you get, whether in the old way of evaluating or with the proposed method for evaluation, when the system is really a human doing the knowledge-based completion, or? So
so what we've done in terms of our human annotation interfaces is we've measured the sort of annotator agreement on these for our interfaces to see how well people are at identifying these relations. So in the TAC KBP setting, they have a sort of pseudo team or pseudo system of having human annotators actually come in and predict relations. We haven't done that. So I can tell you that we have fairly good agreement rates for people both doing the identifying precision. We also have, when we have people sort of exhaustively annotate documents, we find that if we combine, I think, 2 or 3 annotators, we basically predict significantly more facts than the LBC annotators did.
That's helpful to know, but that was not my question. So I was wondering if one of the systems that you evaluated, you mentioned that one of the participants is really like a team of human annotators. And I'm wondering if you observe similar biases to what you've seen with the automated systems when you were measuring the original, using the original metric.
The question there is, how is that data set constructed? So in all of the numbers I showed you, the system, I always had the human system as part of the evaluation data set. In principle, I could also look at, suppose I look at the evaluation data set constructed by everyone minus the human beings. I can look at what that bias is. And if I remember right, that bias is still pretty significant. The humans identify facts that are slightly different from the ones that the systems identify. Okay. So I'll try to go through this section a little quickly, and I basically want to look at some problems with evaluating generation. Remember, my 2 tasks are open response question answering and text summarization. And the question answering task is basically derived from MS Marco, which is a data set of queries given to the Microsoft search engine and a set of top 10 documents from their search engine. They then get like humans to basically go through these documents and come up with sort of summaries of answers. And the way we're going to evaluate the kind of prompt in some sense, the evaluation metric we have for a system on this task is whether the answer provided by the system is correct according to the given passages. And the way we actually do this is we give annotators the actual sort of answer given by a system, and then give them all of the documents, all of the supporting passages, and have them sort of report whether it is correctly answered and actually highlight the justification. This last part of highlighting is very important to get them to do the right thing. Otherwise, yeah, anyways. In the other case of text summarization, there's a number of different ways to try to do evaluation. We are basing ourselves on the CNN Daily Mail dataset, which have sort of multi-sentence summaries. And we have 2 ways of measuring the quality of a given summary. One is kind of like this traditional Likert scale kind of query of, is the summary fluent, not fluent, okay, very fluent. And the other sort of like this. And the other version we have is we actually have them edit the given summary into something that's readable. The highlight is that I think we were surprised to see that the kind of agreement rates for this post-editing, well, if I look at sort of the variance in terms of the prediction, is significantly less than when people are pressing these buttons. This is on the same interface, so I think annotators are taking this. I don't think people will spam these questions and then write some very coherent text. So I think there is fundamentally a lot of subjectivity when it comes to answering questions like, is this paragraph fluent? Which is avoided when you ask them, just make this paragraph more fluent. The kind of fundamental evaluation problem we have is we want to be able to compare two answers given by systems and figure out which one is should be better. In this case, no, yes, and once a SIM card is deactivated. And there's one approach which is exact matching, and I just want to tell you that this is not practical because there are very, very few exact matches between the reference answer and the answers given by systems, even in the question answering task. And the other approach is you use some form of similarity metric or automatic metric. The most common systems that are used are Blue, Rouge, and Meteor, which are these basically based on some form of word overlap. Though more recently, there are some approaches which try to use word vector or sentence vector similarity that we tried with. There are also some learned evaluation models that those models don't apply in our task, and so we don't have enough data to train them. I just want to point those out. The key problem, and this is my favorite graph of all of last year, paper by Novikova, is that if you look at the correlation between these automatic metrics, which is over here, and the human metrics, which is the very bottom, you see two things. One is that all of the automatic metrics are incredibly correlated with each other. And the second thing is that their correlation with the human judgments is between 0 and 0.3, which is not very impressive. There's a little more that we found in our experiments when we were looking at correlations, which is that this correlation also varies across different systems. And that's clearly also part of a problem. We kind of expected this too, but.
Yeah, so with respect to Rouge metric, the original paper proposed that there is 99% correlation between human judgments and the entire mode that's predicted by the system. Is that no longer true?
Yes, I have looked at this. I've seen that result, and I've wondered what's happening there. And I don't know if they're talking about things at a system level correlation, or maybe the instances. I'll also mention that the thing that they're correlating there is content coverage, which is slightly different than any sort of form of quality. And so Rouge has been, in some sense, horribly misused.
You mean they're using Rouge for tasks that it should be used for?
Tasks that it was not proposed for. So it was proposed to basically see how much content in a summary is basically how much content in the documents is covered in the summary. And so it was viewed as a way to do this content, I forget what they called it, but basically content selection, content coverage, without saying anything about the quality of the summary otherwise in terms of language quality.
Yeah, you can't measure the grammatical structure of the sentences because you're measuring overlaps, so that's understandable. Okay, so you're saying that the correlation that you measure, this is your work or? Oh, okay.
So this is prior work. There's also other work for Liu et al. Shows that there's low correlation. There's been even I can point you to other literature where that's shown that Rouge and Blue both have low correlations when looking at other generation tasks.
And when you're specifically looking at things like coherence and readability.
Correct.
Okay, got it.
There's this question of sometimes people view that there's maybe, even though the correlation at the instance level is very, very low, maybe when you average across systems that you see better behavior. And this is a very misleading graph. This is just for the data set that we collected. But the two systems are fairly correlated. So you can, in some sense, these are 2 points. So obviously, you can draw a line through them. But I wanted to sort of contrast this picture here, where you have the systems themselves, and at the system level, what the root score is versus the average human judgment score. And if you look at if you pick apart for the instances of any one system, if I remember right, this is fast QA ext. This is how these if you look at what the distribution of Rouge-L scores for a system that has, like when the answer is wrong versus when the answer is correct. The thing I want you to pay attention to, like even in the ideal universe, you should see one large blob here and one large blob here. What we actually see is that there's a giant blob here, which is, if you think of this, this is essentially false negatives, right? These are things that the Rouge are automatic metric, things are bad, that humans think are good, and the sort of things that are in this space are things that have multiple correct answers, like a surname origin. There are two answers here. There are lots and lots of answers that can be worded in different ways, like the definition of onomatopoeia. And because these scores are so low, you can have really bad summaries that can have a higher Rouge score overlap. This is maybe the majority of this cluster. And so essentially what's happening is across all of the systems, all of the answers for things here, these hard examples are basically given very low scores, and they're kind of excluded from evaluation. If we want to evaluate them, we need to do something here. There's a little further point that's actually best made in an analysis of the duck competition, which essentially shows that there are lots of ways where you can change your system so that you can improve human judgment scores without changing your Rouge scores. There are also lots of ways you can change your Rouge scores, or you can improve them without necessarily improving human judgment scores. And that's kind of what they observed to happen between systems on the duck task. I don't have a lot of time, so I want to kind of highlight that I want to give you a key intuition as to like what our technique is, and then kind of close things. And the fundamental question we're trying to answer is there anything we can do to fix the bias that's introduced by these automatic metrics? We see that they have these very low correlations. We know that they're not predicting sort of system performance correctly. Is there some way we can fix this with human annotations? And the way I rephrase that question is, let's again look at the something that we know by definition to be, or we define to be correct, which is human evaluation. Is there a way we can introduce the automatic metric in a way that could reduce the cost of human evaluation? And the key sort of insight as to like how this might work is this picture where, let's say I've taken my input on as like a line, and this blue curve is the curve of ground truth, like fluency scores or correctness of answers that I want to compute the average score of. And human evaluation says, let's take a sample of these outputs, and we have this space, and we just compute what this mean is. Now, if I have an automatic metric, and the one purpose of an automatic metric is to have some degree of correlation with ground truth. We've seen that it doesn't have a high degree, but we know there's some degree of correlation. Can we exploit that? And the key intuition, or the key intuition, is that if you look at the difference between the automatic metric and the ground truth, because there's this correlation, by definition, it will have less correlation. And so if we take the average of that difference, this is going to be a process that will have less variance. And hence, we can estimate this mean with fewer samples. And so that's the exact estimator that we proposed. We basically went from taking the mean to subtracting off this automatic baseline. There's one trick you have to throw in here, because suppose G is not correlated with your ground truth, then this is sort of like adding noise to your estimate. So in order to correct for that, you have to add the scaling factor, which is proportional to the covariance. We can show that this approach, I just want to, because I've changed notation, etches the human annotation. So there's some noise. This is just a noisy, the sort of measurement of f of z. Think of it that way. And I've just given you this kind of, here's like one estimator we can write down. But we can actually sort of prove that it's a minimax optimal estimator, which means that there's no other unbiased estimator that uses just the human annotations and the predictions of the automatic metric that will have a lower worst case variance. And so Hence, we can actually look at the performance and the variance of this estimator as a way of characterizing the sort of limitations and possibilities of using the automatic metric. We kind of have this measure, which is the ratio of the variances, which we call data efficiency. Just think of this as the relative number of samples you need to collect to achieve the same confidence threshold using this control variance estimator versus the mean estimator. I don't have much time to talk about this, so I will just tell you kind of what these results look like. We've collected data from 4 systems on both of these tasks. And we have about 500 responses each. And in each of them, we collected 2 independent annotations so that we could do bootstrap sampling that includes annotator noise, which is an important factor to consider. So the kind of results are a little disappointing because we find that if we use this method, the most we can reduce in the number of samples we have to collect is only about 15%. And while this seems like it's a very small number, I want to stress again that there is no other way to combine the automatic metric with the human evaluation that can consistently do better than the approach we proposed. So this is really kind of the limitation of what we can achieve with our current automatic metrics and the way we collect annotations. We can sort of ask kind of, what if we improved the performance of the automatic metric? We can easily run this experiment and also punch this through math. And in that case, we can improve our sort of data efficiency from 1.16 to 3. So this is from about 13% to saving about like 30% of your data. Sorry, saving you needing only about 1/3 of your data. The other case is, what if we change the way we're annotating our data? Because even if you have a perfect automatic metric, something that's perfectly correlated, you don't know it's perfectly correlated yet. And so you have to like ask some human beings to find that out. And if they are noisy, then you, again, end up requiring a lot of samples. So I think I mentioned in the beginning when we were doing summarization, we have 2 kind of prompts. One is asking people to match these buttons of how fluent it is. And the other is to actually edit the text. And the key takeaway is that when you ask people to edit text, it has less variance. And so we actually see, you can see these gaps are larger, and we can basically save more data. So there's this second benefit to improving the way we annotate our data. Key takeaways are, in no ways can I say that this technique is something that will allow us to significantly reduce the data we need to annotate. But because we have some kind of theoretical backing, we can also tell ourselves we need to sort of change the assumptions in terms of how we do human evaluation or how we basically measure generation systems if we want to possibly do better. With that, I will conclude and just summarize. The goal of my talk is to basically shed some light on the fact that these existing automatic evaluation methods we're using have inherent bias to them. And if we want to sort of debias them, the approach we propose is by having humans in the loop. In the structured settings like KBP, we're actually able to have significant cost savings. In natural language generation, not so much. And I will end the talk with just throwing up some of the other work I've done and take any last questions.